So this is a video on velocity versus time graphs. What you'll notice here is a set of three graphs: displacement, velocity, and acceleration versus time for one type of motion. So you'll notice that the displacement versus time graph here on the left has a straight line with a positive slope. Okay, this represents a velocity that's a straight line horizontally, because we know that the displacement, the change in displacement, is constant over time. In other words, its velocity is positive, but it's staying the same. So if it has this constant velocity, then we know that its acceleration must be zero. So let's take a look at another type of motion. And in this type of motion, we'll notice that the displacement versus time graph is a curve. Well, if we were to take a look at this and actually graph the velocity versus time for this type of motion, in this case, we'll notice that it's a straight line with a positive slope, just like the displacement versus time graph in our last example. Well, in this case, the straight line positive slope is representing a constant change in velocity over time. Well, a constant change in velocity over time means that your acceleration will be constant. It's positive, so the object is accelerating, but it's accelerating at a constant rate. Well, how would we know exactly what that level of acceleration is? Well, from a graph, we could find that by taking the rise over the run. In other words, taking the slope of this line. So if I take the slope of a velocity versus time graph, if I take the slope of a line on a velocity versus time graph, I can find the rate of acceleration. So let's take a look at this graph, and let's pretend that this graph here is representing a bus. Okay, so it is a bus in motion, and this bus is traveling at 0 meters per second up, and it increases its speed up to 10 meters per second in just 5 seconds. Well, how could we calculate what its rate of acceleration is? Well, again, we would just find the slope of this graph, and so we could take the rise over run. And essentially what we'd see is that in 5 seconds, it went to 10 meters per second. So we'd have 10 divided by 5, and we'd get a value of 2 meters per second squared. So that would be the acceleration from point 0 to point A. From point A to point B, we'll notice that the acceleration is 0 because the velocity is constant. Okay, so we could go through this graph and continue to analyze this type of motion. So the question that I have is, when is acceleration the greatest in this graph? Well, I'm not asking positive acceleration or negative acceleration, I'm just saying acceleration. So what you'll look for is where the line is the steepest. And in this case, the line seems to be the steepest from point B to point C. We'll notice a change of 10 meters per second in only 3 seconds, albeit a negative one. So we'll have a negative 10 divided by 3 for when we were to find our slope of this line. And we'll get a value of negative 3.3 meters per second squared. So just because the bus is decreasing its speed doesn't mean it's not accelerating. It's just accelerating in the negative direction, or something we sometimes call deceleration. So let's take a look at this and say, how far does the object travel in this? So now let's look at this in terms of displacement. How far does the bus travel throughout the entire journey? Well, what you might remember from class is that the area under the curve equals the displacement. So if we wanted to find the total displacement here, we would have to find the area under the curve. Well, how do we do that? Well, let's start. So first, we'll divide this area into pieces. First, we'll make a nice little triangle here, and we'll make a rectangle here. And we'll start to calculate the distance between point 0 to point C. But let's start from 0 to A. And I've made it into a nice triangle here. So the first thing we need to do is to find out what the area under this curve is right here, under this line. And one way we could do that is just to count the squares. Or what we could do is just use our formula for a triangle, which is 1/2 base times height. So under here, what you'll notice is that the base is 5 and the height is 10. So that would be 50. But we want half of that because it's a triangle. So what we would know is that underneath this curve, we have a total of 25, and that's going to be the distance traveled by the bus from point 0 to point A. It's 25 meters. Well, we can continue doing this over here. Now this is a rectangle, so this is just going to be length times width, as the formula for of the area of a rectangle is length times width. So in this case, the length is 10 and the width is 5. So from point A to point B, the bus traveled 50 meters. So from point 0 to point B, the bus has traveled a total of 75 meters. 25 meters from point 0 to point A, and 50 meters from point A to point B. Well, I can continue on and to do this from B to C. In this case, my base is only 3, because I'm going from 10 to 13. My height is again 10 meters per second, so I have 30 times 1/2, which means the bus traveled 15 meters in this time. You can continue on to go on and try and calculate the area underneath this section by dividing it into chunks just like this and finding out what that total area is for yourself. One other complication we might have with these velocity versus time graphs is if we don't have straight lines. Unfortunately, reality doesn't always work in straight lines, and acceleration is not always constant. So sometimes we have changing acceleration. And when acceleration is changing, our velocity versus time graphs are nice and curvy. So what we have to do in order to find the slope, we can't do rise over run because it's not a straight line. So what we have to do instead is to draw a tangent. Now a tangent is something that you just have to guess what it might be. You have to take a point somewhere on your line, and it has to be a straight line that touches this point but nowhere else on your graph. And it just has to be a best guess of what the direction of this curve is taking. So it was over here, it is here, so you can just take a best guess by drawing a line across for here. At this point here, A1, we've got to think this is where the point is. This is where it's intersecting the graph. So the tangent at this point is here. And what about right over here? At this point, it's flat. So what do we know at this point? Well, at point A1, let me get that into a different color. So at point A1, the velocity is still increasing. So you notice that we have a slightly positive acceleration. Well, what about here? Well, at this point here, A2, you could see that velocity is no longer increasing. So at this point right here, we have a constant acceleration in a straight line. Well, what about down here on point A3? Well, what we'll notice is that the tangent has a negative slope to it. Therefore, it is the velocity is decreasing over time. And in order to find what the exact value of this acceleration is, you'd have to take the slope of the tangent line that you drew. Now, since this tangent line is just a guess that you're making, everybody's going to have a slightly different answer. But we should at least realize that by point 83, it's a slightly negative tangent. No one's going to come over here by A2 and draw a line like this because it intersects your graph, and so that's not correct. It has to be a line drawn so that the only point it touches on your line is your point of interest. Okay, I hope this helped. If you have any more questions, we can deal with them in class. Cheers.